we go. Okay. So this is more or less where we were the last time. I think what I'll do is break this up. My objectives are to get through factor congruence and then talk about bifactor rotations that we can do and look at what those look like, and then introduce the idea of target rotation. Because target rotation, I think, is a really nice way to do analyses if you started out your study thinking that maybe there are some indicators on the factor. It kind of eliminates all of that trial and error and trying to look at things. So that's where I'm hoping to get to today. As I mentioned last time, since I'm sort of a rotational anarchist and encourage you to do all kinds of rotations, at the end of the day, you might have many different types of rotations, and you might wonder, well, is it really, worth it, or are these rotations very different from each other? And similarly, if you're doing an article and you're using exploratory factor analysis, you probably want to be able to satisfy an editor and a reviewer that the picture is not going to change that you're summarizing very much if you did make some other different choices. And factor congruence coefficients are kind of a nice summary way to address those side analyses, maybe put them into a table that accompanies the submission as a reviewer's supplement. And it also makes for good supplemental tables at the end of your dissertation or your thesis. So the idea of factor congruence is inspired by our good old friend Ledyard Tucker, who's kind of this really smart guy at the University of Illinois who had a lot of insights that seem to escape other folks. The idea of factor congruence is a pretty easy one, though. Specifically, what I'm going to do is to take the loadings for one of my rotations and multiply it by the loading from another rotation for a given variable. And I'm going to add them up over all of my variables. And then down here in the denominator, I'm going to take each of the loadings for that variable squared, add that up over all my variables, and do the same thing for the loading squared for the second rotation. Now, if you're looking at that, that kind of looks a little familiar because when we were talking about a correlation coefficient, that was the covariance divided by the standard deviation of x, standard deviation of y, or in other words, the square root of the variance of x, variance of y. And if we go back to our formula for the correlation coefficient and we stick in the definition of the correlation, we can kind of see that a little bit better. So the difference between a congruence coefficient and a correlation coefficient is that if I were calculating a correlation between two sets of factors, I would be subtracting out the average factor loading across all the variables. And that's not done in the congruence coefficient. So, it's similar, but in addition to looking at the similarity, it also takes into account the relative magnitude of your loadings as well. So for example, if you have a 0.8 loading and the average loading across all the variables is 0.3, the correlation coefficient would take that into account. Now that formula is pretty easy to work with. And if you play with Excel, you can cut and paste the loadings onto a spreadsheet and multiply the loadings across and add them up and calculate this congruence coefficient by hand. If you're playing with R, there's a nice little package called factor congruence, which will do that for you. I mean, it's not rocket science, as I mentioned. So in the example that we had above, if we were doing the two-factor solution that's kind of oblique, I could calculate a Varimax and a Promax and a geomin oblique rotation. And this is what the congruence coefficients would look like. Now remember, in that example above with the two factors, these are the two factors that are really highly correlated with each other. And so as I'm looking at factor one and its congruence with factor two, they look pretty similar under Varimax rotation, because remember, Varimax rotation assumed that factor one and factor two had zero correlation between them. On the other hand, Geomin and Promax, those two things assume that the correlation between the two factors exists and is non-zero. So for that reason, in F1, in the Geomin rotation, the congruence between factor one and factor two is pretty low. And the same thing for Promax. If we're going to address the question of how similar are these solutions to each other for the two oblique models, factor one from the Geomin and factor one from the Promax are pretty much the same thing. And similarly, factor two from the Geomin and factor two from the Promax, also pretty much the same thing. So your conclusion would be, in this little example, it doesn't really matter at all whether you've got a Geomin or a Promax rotation. The story is a little bit different for Varimax because, largely the first factor one turns out to be kind of factor one for those two, and factor two looks like factor two for those two. But, because Varimax assumes no correlation between the factors, you've also got these other congruence coefficients. So in terms of an interpretation, it seems that, the groundwork is a little bit stronger for believing that there's an oblique solution. Okay. So I have mentioned earlier that in addition to the rotation methods that we've talked about before, which are attempts to look at simple structure, correlated factors, and trying to find solutions that hopefully where the items only load on one, with Geomin actually more successfully recovering rotational loadings when that assumption is not met. It's also possible to look at bifactor models. And the reason that you'd look at bifactor models is that the simple structure, I'm sorry, it jumped over to bifactor models. That's what I get for being so hyperlinked inside the PDF. The reason you might want to look at bifactor models is maybe you have a mono method multi-trait study. That is, maybe all of your items load on one big factor because they're all, say, survey items, or they're all 5-point Likert scales. Or it might be the case that the phenomenon that you're looking at actually has one general predisposition and then little subclusters that relate to items. So if you're looking to give some examples that are not psychopathology, if sometimes when you're writing an achievement test for a class, or sometimes when you're writing a survey where people are supposed to reason through different scenarios, a bifactor rotation might be helpful because maybe the first 5 items of your survey deal with, in your business, this, here's a scenario where you're having the following issue with an employee, and those first 5 items deal with story 1, and the next 5 items deal with story 2 and 3 and 4. And it doesn't really make sense to look at an oblique solution there because the construct that you're interested in is this general thing. And in the same fashion, if you're doing, say, a classroom achievement test, there might be math problems where the story has more than one item. So in terms of that, there's 2 models out there for the same reasons that Varimax and Quartimax are kind of different rotations you want to consider. There is a bifactor Crawford-Ferguson Quartimax and a bifactor Geomin that you can look at. And what that program is going to do is to try to extract one factor out here with loadings that are the biggest, and then a bunch of little baby factors that will capture the other model. Now, in the context of rotating, sometimes this second factor is going to be the fourth factor. So in this case, under BF Quartermax, I got a 0.41 on the fourth factor, and I got a 0.49 on the second factor with bi-geomin. So the labels might switch a little bit in terms of things. So you have to look at what the numbers are. And similarly, I have a 0.83 over here, and that's on factor 2, and 0.82 over here, and that's on factor 3. But as a result of this model, it's going to try to extract this general factor, and that general factor seems to be, again, the social items, and then downstairs here, the pleasure items, or how it makes you feel to be intoxicated. Because, and that kind of makes some sense, because when we did the oblique rotation, these items, this factor tended to be correlated with this factor. And these other loadings do not show simple structure because, again, that first factor is trying to take everything out that it can. And as we're inspecting that first factor, it looks like there's a fairly close correspondence across the loadings in the two. So when you're doing a bifactor rotation, that big first factor has no correlation with others of these little subfactors down here. But the little subfactors down here can have a correlation with each other. So, generally speaking, in this application, these two rotations look pretty much the same. And I can come back and look at my congruence coefficients between the bifactor geomin and Quartermax and find, as I was saying before, things on the Quartermax rotation tend to load very similar with, that's the one factor on the Quartermax, and factor 2 on the bifactor Quartermax tends to correlate with factor 3 into the bi-geomin. So, this is an exploration. It is a way of thinking about these things. It is not the way of thinking about these things. Notice that we don't have a way at this point to do a rotation that would correspond to, say, a random intercept factor model. So if we go back and kind of think back in our heads to random intercept models, a random intercept model had one factor where all of the loadings were fixed to 1 with a freely estimated variance, and another factor with a factor variance fixed to 1 and all of the loadings free, and no correlation between those two factors. Well, under both of these bifactor models, you're kind of smushing those two things together. So the only way that you could proceed if you thought there was a random intercept factor going on is to go back and do a target rotation or using exploratory structural equation modeling. And we'll talk about kind of how to set that up later. Conversely, the other thing to keep in mind is for these subfactors, that's also going to assume that one factor fits everything. And with 4 indicators, you could just as easily also say, maybe instead of one factor being here, there are in fact 2 subfactors, one with all the loadings free and one with all the loadings fixed to 1 with a variance free, or a tau equivalent model. So all of these rotations that we have talked about, our guidance is, generally speaking, oblique factor solutions for simple structure are preferred. Geomin works pretty well in practice. Doesn't tend to look that much different than Varimax, though. So if you stumble on a reviewer who says you must do this because it's that, you can probably calculate congruence coefficients and present it, or you could just yield and present the Varimax rotation. Now, sometimes when you're doing your study, you might say, especially when you're doing the rotations, you might say, I really think that I have a theory, or there's somebody out there who does have a theory about what this factor solution should look like. And some examples of that happening are when somebody else has done a scale and you're doing a scale as well. Like often in our department, someone publishes a scale and it's got way too many items. So we attempt to select out the best performing items and then produce a scale with a fewer number of items. And you want to satisfy yourself that, maybe in the population that you're looking at, that the factor structure looks kind of the same. Well, if your previous researcher published their rotated solution, it's going to have some zero loadings on some of the factors after it's rotated. And target rotation is a way for you to plug in that information and say, dear computer program, give me a rotation that looks, say, like a geomin rotation, but in which I'm setting some of the loadings to be zero. Now, target rotation was proposed by Michael Brown, and he's kind of another one of those scary, smart people out there. And what he had said was, I'm going to specify in my analysis, try to make this loading as close to zero as possible. And in order for us to do that, we're going to have to figure out how many loadings in the rotated solution we're going to have to set to zero. So when you've got m factors and you've got an oblique solution, you're going to have to set m times m minus 1 zero loadings. And similarly, if you've got an orthogonal solution, it's going to have to be m times m minus 1 divided by 2. There's nothing to guarantee that the target values you're going to see are going to be exactly zero. You might get a number that's a little bit different than zero. And when that happens, maybe this rotation isn't good. But on the other hand, if it's pretty close to zero, you might want to say, well, it's pretty close. And generally speaking, this looks kind of like what I'd like to see. And you can then go back and after doing your target rotation, estimate congruence coefficients with your target rotation and maybe a geomin oblique solution. Now, here's a little bit of math about what the target rotation is doing. So if I've got m factors and I've got p variables, my solution is going to take the loadings minus the target value, 0 or not. In other words, it's 1 if it's a target loading and 0 otherwise, squared and multiplied by a. And there is a paper that you can cite which talks about Monte Carlo methods for comparing the relative merits of target rotation to existing geomin and ESEM that we'll talk about later on. And target rotations are pretty easy to do. Especially if going into this in your literature review, you found somebody who says that these items should load on a given factor. So let's take a look at a little bit of M+ syntax on that. And the reason that I go into M+ is this syntax is different than the syntax that you're going to see on other programs. And it's also different than the syntax that you would need to do a straight exploratory factor analysis in M+. So, excuse me, after putting in the data set and then the title and so forth, your analysis section would say rotation equals target. And after that, you'll list the factors that you have. So recall in a straight exploratory factor analysis, you didn't have a model statement. You just said, give me a 1 to a 4 factor solution. So we list the factors that we think underlie the data. And then inside of this, for a given factor, this is saying, hey, go ahead and estimate for this first factor, loadings on all of these items. But in this second row, set the first variable's target to be 0. And that's telling the computer program, please rotate so that G, Q, and V are as close to 0 as possible. And the end of that factor loading has to have this little bit of syntax of a left paren star t right paren. And that's just a way of telling the computer program, oh, by the way, this particular factor contains target information. And secondly, I can do that for the second factor, saying, oh, this first item has a target of 0, but freely estimate the rest of these. And the third factor, the same thing. And the fourth factor has freeloadings down there. So if we do that target rotation, these are the numbers that I get out. And you can go back and compare this with the Geoman rotation, but what we have here looks a lot cleaner. Notice these numbers are a lot closer to 0 than they were before. And these numbers are a lot closer to 0 than they were before. It tended to clean things up. The fit of this model, by the way, folks, is exactly the same as the fit from a standard rotation. So, target rotation is a way for you to do that stuff that, quantitative psychologists, ran off into their room with protractors and rulers and arrived at via physical inspection. So down here at the bottom, you can see that the correlations between the factors are now a little bit increased. And that's because in your target rotation, you zeroed out some of these loadings. So whatever those non-zero loadings were in the Varimax and Geoman rotation, the only place that those associations can go in is down here. So I'm hoping, those of you using M+, that this is, kind of a tool that would be semi-useful to you. And again, as I mentioned before, you can take this rotation and go back and calculate concordance indices with some other rotations to get a sense of exactly how different this rotation is from other things. This section that I have here is tying things together for us, not in the sense that I'm giving you a whole bunch of rotational criteria to consider to make things even more complicated, but I thought that the Crawford and Ferguson article was kind of a useful one for talking about a whole bunch of rotations. Crawford and you'll find in the M+ and the factor rotation procedures in R that they'll talk a lot about the Crawford-Ferguson criteria. And Crawford and Ferguson introduce a weighting thing, kappa. And what we're talking about is the rotations, the desired rotation is composed of one factor involving kappa and another factor involving 1 minus kappa. And I'm again summing over all my factors such that I'm not double counting the factors. That's the reason for this not equal sign. And this is my raw and my rotated factor. And the reason I'm talking about this model for you is it incorporates as special cases many of the individual rotation criteria that we talked about. So if, for example, I set kappa to be 0, this Crawford and Ferguson rotation gives me direct Quarterman as a rotation. And similarly, if kappa gets chosen to be 1 minus p, 1 divided by p, where p is the number of variables, I get orthogonal CF Varimax, which is a kissing cousin to the Varimax rotation. And if I take kappa to be m divided by 2p, that's going to give me Equimax. So all of these things are special cases of this. And finally, if I come back in and do 1 for kappa, I get the parsimonious factor analysis. So it's, it's just kind of a nice thing to notice that just the same way as when we talked about loss functions, there's a couple of ways to write it. When you write rotations, this is one great big model, and it has as special cases, several things that we already know about. So exploratory structural equation modeling is a way of trying to get at the idea of rotation within a multi-group model. So one way of thinking about an exploratory factor analysis is we'll go back and use the items from the subscales of the reasons for drinking scale. And you could then do an exploratory factor analysis of just the women and just the men, and satisfy yourself that you have the same numbers of factors going on. At the end of the day, though, just looking at a separate exploratory factor analysis doesn't really do a good job of telling you whether those factors are the same things across groups. So I could say that maybe across my two groups, the factor loadings, the errors of measurements, and the intercepts are all the same across men and women. And down here, this is the code in M+ that I wrote. So here's my title, here's my data, here's my variables. And I'm going to be analyzing this as a multi-group model. So I want to use the sex variable. And down here I say, I'm grouping the data. You know, these are the females, these are the males. And the code for the rotation says, I've got 4 factors going on, 1 through 4, and here's all of the loadings. And the factor means are fixed at 0. And then down here, here's all of my males. And that then, you know, says I've got factor 1 through factor 4 on the males. And that's going to give me and again, I'm going to fix the means of those to 0 and fix the variances of factors to 1. And I walk through exactly what's, you know, just what I said. And M+ is going to default to a geomin rotation for this. So downstairs, when we're factor analyzing, we can fit other models as well. So I guess the way that I'd organized this discussion was to talk about each of the invariance hypotheses first. I'm sorry to be skipping around here. If I want, I can say that the factor loadings, the intercepts, and factor variances are invariant, but that the means are variant. So what this would say is, in factor 1 and factor 2, there's the same loadings and factors going on, but maybe the means of the, in this case, reasons for drinking variables are different across men and women. Well, in this, to set the covariances between factor 1 and factor 2 to be the same, you come back upstairs and you replace lines 25, line 25 with this code. And that's going to go in and change all the covariances. If I'm taking the factor loadings, the errors, and the intercepts to be variant, I'll set the factor variances to be this. I'm sorry, that's the same code as before. And if I want to say that the errors are variant, I fit model D above and I put in this line. So maybe it would be helpful next time to actually go through the programs and look at the analyses, but if you can bear with. And if I've got model E above, I'm going to take this line out and add in these lines, and this is going to allow the error variances to be different across groups. And finally, if I've got the loadings, intercept, means, and variance, in other words, everything is different, I'm going to put in 25H, and that will accomplish that. So, I talk about each of those models as well, but probably, this is a picture of the analysis as it looks in its larger proportions. So if I've got in model A, everything's going to be different. That is the loadings, the intercepts, the factor covariances, and the error variances. That gives me this chi-square. And here's the rest of my fit statistics. If I'm just saying the loadings are going to be the same, but the factor means are different and the intercepts are different, that gives me this chi-square and BIC. If I've got loadings and intercepts to be the same across groups, but the factor means are set to 0, that gives me this. And if I've got loadings and intercepts and variances and factor covariances the same, but the factor means are different across the two, that gives me this. Now, because I've got a huge data set, all of these chi-squares are going to be significant. So one way for me to judge against these models is to look at the BIC, and the lowest value of the BIC is preferred. So in terms of a multi-group invariance analysis, this is telling me that I can treat these factor loadings as the same and the intercepts to be constrained across the two groups, but the factor means can be different and the error variances can be different. And at the end of the day, that then tells me my conclusion is that, yes, there are 4 factors going in the data on the basis of my exploratory factor analysis. And yes, the loadings appear to be representing the same quantities across males and females, but the factor means are different, meaning that men have more reasons for drinking across all 4 subscales than women. And coming down and making more restrictive models, like setting the factor means to be 0 and having them be the same, gives me a higher BIC. And similarly, for these other analyses as well, if I'm now going to let the factor means be different, but constrain the error variances to be the same, this is my BIC value. And if I've got loadings, but not intercepts, but factor variances and covariances, but the factor means at 0 and the error variance is at 0, here it is. So, there's some pretty clear evidence that I don't have the idea that measurement error is the same across men and women, and this ends up being my preferred model. In terms of TLI and CFI, those are kind of acceptable values. I get pretty much the same solution using the AIC. As I mentioned before, the BIC tends to perform better in Monte Carlo studies. The RMSEA is 0.06, which is a little bit higher than what people are often used to seeing, but for all of the candidate models here, I've got a 0.06 value going on. And that's the discussion for what I have said here, and here are my recovered parameters. So here are the loadings for the first factor, and I bolded the statistically significant loadings. And here are the intercepts. Now, the intercepts were set to be equal for men and women. So those are the manifest variable intercepts. The error variances were free. So these are the manifest variable variances across the two groups. And here are the variances and covariances across the factors that I had before. And then downstairs, here are my means. Well, as we talked about in the multi-group model, if I'm freely estimating the manifest variable intercepts, but constraining them to equality across groups, I need to adopt a reference group. So in this particular study, I chose women to be the reference group. And the freely estimated means on the 4 factors for the men are here. So this last factor, just because I like the taste or the flavor of it, seems to be a lot higher for men. Well, I can convert, since this has a mean of 0 and a variance of 1, I can convert this 0.1 into a percentile. So, that kind of gives you a way of talking about the magnitude of the differences of the average male relative to the distribution of women. So next time we'll go through the M+ thing and we'll actually go through the code. But in broad brushstrokes, this is where we're wanting to go in terms of a way to rotate things and do it as multi-group. To my knowledge, this is kind of your place to go to look at how this is set up, because I've not seen any other books out there or even on the web that talk about setting these up. There are published examples, though. So to kind of end with this part of it, there's a theme, namely that we tend to take our variables that we have and think about them in some parsimonious fashion. The unrotated solution out of a factor analysis doesn't make any sense because it's just a serial extraction of numbers from a matrix where the first factor gets the first crack at things. And so going back to the chapter on parsimonious models, those are our patterns for looking at how we might organize our data. And current default behavior of exploratory factor analysis is to say, I'm going to look for simple structure. And, if I say so, geomin or promax rotations that would allow for the correlations to exist between the factors. But that's not necessarily the only choice you have. So as we talked about, random intercept factor models are not considered. And you could specify those as a confirmatory model as a follow-up to a provisional exploratory solution. If somebody else out there has a rotation that they've produced, you can use target rotation. And if you have a lot of data and you're looking across multiple groups, you can set up this code to look at the possibility that a common rotated factor structure exists in the data, but that members of groups vary in specific ways across those rotations. As we saw in this example, it looks like psychometrically error variances are different across the groups, and there exists significant mean effect differences across men and women. So one of you is, for example, looking at a really huge data set across many countries. Well, if you were to do a multi-group exploratory factor analysis, at the end of the day, you can say things like, oh, well, and I think some of these were belief in institutions and maybe political ideology. Maybe political ideology varies across countries, but the items assessing that ideology are functioning kind of the same as loadings. So there's a couple of nice papers out there. Michael Brown did a nice survey, and Ginrich did a nice exposition of how rotations happen. So if you really want to go into the math and rationale, those would be the two places that I would start. So at this point, we kind of come to a divergence of software because in R, if you're using exploratory factor analysis, you're doing just an exploratory factor analysis. And there's no way to say things like, well, I have over here a criterion I'd like to predict to that. Or I have a covariate that I want to put in the model. And also, if you're doing a multi-group factor analysis, there isn't any way inside of R to do that. M+, however, as we've seen in the code here, does let you do that. And if you have covariates, or if you have other criteria you want to include in your model, say factor 1 through factor 4 in their rotated form are now predicting, say, alcohol consumption at some later point. All you need to do inside of M+ is to read in those variables and then say these variables are predicted by F1 through F4. So your model can come out looking like a hybrid of exploratory factor analysis and confirmatory factor analysis. But that's only going to be possible on that M+ platform. So I've been talking for a bit, Next time we will go through M+ code on the target rotations and the invariance questions so that we can kind of look and ask questions. It seems that when I'm actually looking at printouts, questions happen. The next topic that we'll be getting into, hopefully, next week, will be categorical dependent variables. And categorical dependent variables are the last thing that I want to address to you. And at the end of the day, they're kind of a simple thing inside of Lavon or M+, in that you merely need to say, oh, this variable has an ordered categorical variable. There's a bit of theory that underlies that. And, I have to kind of explain that. One of the nice things about that is categorical dependent variables with structural equation models actually correspond to the things that you would see if you take a class in item response theory. So that's kind of another reason that this is a connection with other courses that you might be doing in graduate school. So as you're reading that, take a look at it. So start to get into that over the weekend. This is now November, and I think what I'll do is to stop the recording here.